All right, thank you. I'm Henry Belinsky. I'm the CEO and founder of MicroTau, where we print nature's surfaces to solve human problems. There's meant to be a subtitle of this, which is Sharks on a Plane, exclamation point. I didn't actually put it in, but it's there in spirit. Okay, so what do I mean by nature's surfaces? You may be familiar with some of these things, but essentially, in fact, I know a number of talks today have already referred to some of these surfaces. But over millions of years, nature's developed these different functional surfaces that solve problems. So you may be familiar with things like adhesive gecko pads with switchable adhesion, anti-reflective moth eyes, lotus leaves that are super hydrophobic or self-cleaning, pitcher plants, very slippery lubricant-infused lips which have anti-fouling and antibacterial properties, namid beetles that can harvest water from the desert air, or sharks that swim efficiently through the water. These are all properties that arise, at least in part, due to microscopic patterns on the surface of that plant or animal, and we've invented what we call nature's 3D printer to print those structures, replicate those useful properties. So aviation and shipping have a burning problem. Specifically, it's a burning fuel problem. So between these two industries, every year they're burning over $300 billion in fuel. That number's gone up since I made this slide. In case you weren't aware of fuel prices, producing almost 2 billion tons of carbon in the process, and these are industries with really razor-thin margins. So the lion's share of this fuel is being burned to overcome drag. So you're burning fuel to push your plane through the air or your ship through the water. And despite the fact there are clear economic and environmental incentives for these industries to decouple from fossil fuels, so most airlines in the world have committed to carbon neutrality within the next decade or decades. There's no clear way that they're going to be able to decouple for the next few decades, if for no other reason, putting aside perhaps the challenges to do with electric aviation or hydrogen-powered aviation, there are trillions of dollars of these fuel-burning assets that aren't going to disappear anytime soon. So nature has a solution for this problem, and we copied it. If you look at the mako shark, which is the fastest shark in the world, under a microscope, it's covered in thousands of these microscopic grooves called riblets. If you ever touch a shark, you know it feels like sandpaper as opposed to feeling smooth. Counterintuitively, that's because it's covered in these riblets that actually make the shark more efficient. So riblets reduce friction drag by up to 12% in air and water. And we manufacture a riblet product that you can put on aircraft or boats to reduce drag, save fuel, and decrease emissions. So across these two industries, we can save about $34 billion a year in fuel and over 200 million tons of carbon. Of course, in principle, if it moves through air and water, we can help improve efficiency. So there's a host of other applications. Commercial aviation shipping really is our focus at the moment, but some of these will be good proof points that we can get as a demonstration to get to these larger industry applications to have the impact that we need to make. So our technology, what we call nature's 3D printer, a more of a mouthful version of describing that is direct contactless microfabrication, or DCM for short. It's essentially a modified photolithographic process where you start with an untreated surface, so anything you can coat, really, we can apply to. We've done plastics, composites, metals, top coats, wood, textiles, but largely now we're doing this on an adhesive-backed film, so we can prefabricate and stick it onto different surfaces. We apply a UV curable coating. It's just a paint that dries instantly, or in a fraction of a second, when you hit it with ultraviolet light. In the photolithography world, you probably know this as a negative photoresist, or the umbrella term is a photopolymer. But UV curable coatings are used in a range of different industries just to improve throughput. So now we have a coated surface. Instead of blasting with UV light in order to cure it quickly, we have an optical system that projects that riblet sharkskin pattern into the surface and traverses across in a continuous fashion. This, similar to photolithography, will only cure the material where the light hits it, but critically it grows the structures within the material. This is part of the sort of special sauce of this process. It's mediated by something called oxygen inhibition, so if people deal with negative photoresist here, they may have encountered that problem before, but we leverage that to be able to change the designs, effectively making this a 3D printing process on that micro scale, but it's on a single step. We're not printing layer by layer by layer, which is your typical 3D printing process. Then we develop, same term as in photolithography, to remove that uncured material and reveal the riblets printed directly onto, say, an adhesive-backed film out of a polyurethane aviation top coat. So this is the material we're printing out of to develop our aviation product. So our competitive advantage really is this fact that we grow with light. This means that we can produce double the savings of alternative technologies, so we can do these complex designs where they slope up and down and interleave with one another, or make very high aspect ratio designs which are known to reduce drag better. We can rapidly iterate, so sort of the next best manufacturing method known for making these kinds of structures, you're spending 5-6 figures to make a single master to be able to then replicate these structures. Whereas we do hundreds of designs in a single print just by changing our light field and our print parameters. And then finally, this obviously has to be a scalable manufacturing process. So we've just finished our first 100 square meter production run. We'll be doing about 400 square meters next year for a full-scale flight test, and we need to get to tens of thousands of square meters to cover the global aviation fleet. And this has been enabled by ANFF. So we got our start back in 2016, winning a contract with US Air Force Research Laboratory. And since our founding, we've been using ANFF's Research and Prototype Foundry at the University of Sydney, what was called the Sydney Nanoscience Hub at the time. I should have found an old photo of me wearing the clean suits when I went in and out of there. I no longer wear the clean suits. But the Foundry has made custom optical components for us, which has been really critical for us. It's a crucial part of our manufacturing process. And having something which is down the road from us, we can get there in 5-10 minutes or hop on a train and get there, have that input, that feedback, and rapidly create new designs is one of the key competitive advantages that we've had. And as a result, we can rapidly produce new riblet designs at a cost and a speed which is orders of magnitude lower and faster than our competitors. So our traction to date, we've won over $5 million in contracts and competitive grants. We've demonstrated 7% savings in multiple tests with Lockheed Martin. We're actually up to 8% now with some further testing. We've had 2 patents granted on the DCM technology in critical subsystems in a number of jurisdictions. We have a small-scale manufacturing facility in Sydenham, next to Sydenham Station. And we completed our first main flight test recently. If you ever watched the Red Bull Air Races, this is Matt Hall, the Red Bull Air Race World Champion, and that's our riblets on his wings, making it more efficient. So what's next? We just completed our first institutional capital raise. So off the back of that, really our focus is to get our commercial aviation product ready for certification and rollout. So we're launching on unregulated aircraft, like that racing aircraft I just showed you, qualifying for commercial aviation, so we're working with one of the 2 big aircraft manufacturers in order to make sure we meet the material requirements of what an aircraft goes through, which is some pretty crazy material tests that we need to go through. We'll be signing a commercial deal with our first commercial aviation partner to go to market, as well as increasing our manufacturing capacity, as I just mentioned before. Secondarily, early last year, we developed a new material which opens up maritime as a space for us, essentially still making these riblet structures, but a material that's prevented fouling. So this has been down on the shark nets in Watson's Bay for about 14 months and still prevented fouling. And so, to close up, we've only scratched the surface of nature's surfaces. So we've talked about shark skin, drag reduction, improving efficiency on planes, boats, really anything that moves through air and water. But as a platform, we want to be making surfaces that can reduce water scarcity, decrease infection of medical devices, self-cleaning coatings, anti-reflective surfaces for more efficient solar panels, or the next generation of robotics. Nature spent millions of years solving these problems with microscopic patterns, and we can print them. Any questions?
Thank you very much. So we do have time for 1 or 2 questions. Who would like to ask a question?
Would you like to say a couple of words about the patents? Are they related to the fabrication process or the patterns themselves, or what?
So it's the fabrication process. So first is about the fundamental DCM process and this fact that we can grow things with light. Second is about the optical system that we have, which allows us to make this single micron irradiance profile with a depth of focus of up to 10 millimeters. So really robust for low cost, scalable manufacturing. The designs are public domain, but we are developing new designs with Lockheed Martin that we'll see how they go.
Yes.
My question is about the scale of these things, because on golf balls, I assume it's the boundary, you get rid of the boundary layer. And the dimples in golf balls are much bigger than the scales that you're looking at for aviation at least.
Yes, so they work in a different way. The golf ball dimples is about delaying flow separation. This reduces friction drag in turbulent flow. Basically you get hairpin vortices, which are little vortices with a diameter about the width of a hair. You make the riblets narrower than that and excludes them from the surface. It scales with wall shear, which is the tau in MicroTau.
Awesome. Final question.
Thank you. I have a question about the durability of your films, because they're exposed to the elements, sun, and all of that. Have you tested that?
Yeah, so we're working with, as I mentioned, one of the original equipment manufacturers. There are two big aircraft manufacturers. And there are material specifications for different coatings or films that are allowed to go into an aircraft. So we have our own materials testing facility. There's things like a QUV weatherometer, which is like a tanning bed you never want to go inside. It has really high intensity ultraviolet light. You do temperature and humidity cycling, which simulates what an aircraft experiences over many years. We do things like abrasion resistance, impact resistance, chemical resistance. There's a whole suite of tests that basically say this should be allowed to go on a plane.
Thank you very much. Can we all please put our hands together for all three of our speakers today? Thank you so much for your patience.